Welcome back, everybody. So let's take it from this cliffhanger on this absolutely awful complexity that we don't like at all in big data, quadratic, not good at all. Can we do better? Yes, of course, the answer is yes. That's the whole point of the cliffhanger. And there is a beautiful approach that actually happens everywhere in a lot of different technologies. It appears in information retrieval, happens also in white column stores and so on. It's called logarithmic merging, or the name of the data structure would be log structured merge trees, LSM trees. And it solves exactly that problem. When you have to consistently have new data arriving and you need to merge and merge and merge and merge, is there any way to do it efficiently, more efficiently than this periodic remerging of n postings? And so here's the idea of LSM trees, or logarithmic merging. Let's say I start from scratch, absolutely no data, empty index, and I start gathering some incoming postings that arrives from people who start to create web pages. Let's say it's in 1989 or 1990. So I have n postings that have arrived, and that gives me a standard inverted index, quite small. And all I do is I just store it on disk. And that's going to be known as my level 0, right? Level 0 of my LSM tree. And that's one standard size, standard inverted index. And then people continue to use the internet and to create new content. And I have, again, a full memory, roughly of the same size. It's this n. I called it n, so that's when I stop it. And then I'm going to again push it to disk. Actually, there's a name for that. Some people call it flush. In the context of white column store, we flush the content of the memory to the disk. Except that, technically, I already have an index of that size on disk. And so what I'm going to do is that instead of creating a second index of that size on disk, I'm going to merge them into an index of size 1, of double the size. Sorry, that's level 1. Right? So now I have one index of 2n postings, and I put it back on disk. I can even do that efficiently without putting it in memory. That's, again, this second part of the merge sort idea, and that we called compaction. Right? So that we call flushing, that we call flushing, and that we call compaction, the idea that we merge this to an index that is double the size. So far, so good? Right, so now I have one index on disk that's double the size of what I originally had, level 1. Now I have, again, new incoming tokens or postings. So now, again, the memory is full, so I'm going to flush it because there's nothing of at level 0 at that point, so I just flush it. Now I have 2 indices, but notice that one is the standard size, one is double the size, right? So technically, we have 3n postings at that point, n plus 2n. Who is with me? Right, very good. So now I have another posting, another complete index that fills the whole memory. There's no room to flush it at level 0, so I need to compact it to level 1. But again, there's no room either here, so I need to build now the quadruple the size, right? And now I can have a compacted index that is 4 times the size, right? And then you probably see how that goes. And again, I flush them. And again, I compact it, and now I have 2 indices, one of size double and one of size quadruple. So now I have 6n. Then I flush again. Then another one, and now you probably see what's going to happen, right? We merge again, and we merge again, right? So now, 2 questions. Yes?
Take it a little bit slower, changing the slides because I'm doing.
Yes, absolutely. I noticed that it's basically this new technology that we're using that it's flickering. Yeah, I will try to take it into account, find a way to reduce that. Yeah. All right. So slow. We merge. 2n. It's more pleasant when it doesn't flicker. There you go. Then you merge, and so on. So now 2 questions for you. First question, who sees that we are just counting in base 2? You see that, right? This is basically it. It's basically a binary number in base 2, except that it's mirrored, that the lowest powers are on the left, sorry, and the highest powers of 2 are on the right. So it's just a mirrored version of a number. So it's just counting in base 2. That's the pattern. And the second question is, who has ever played 2048, the game? Right? A lot of you. So this is basically it. That's basically the 2048 game that we are playing here. We're just merging powers of 2. So that's a good way. That's one of your predecessors who observed that, and that's absolutely correct. Okay, so who understands LSM trees? Right? Again, 2048, you got it. Very nice. All right, so that's really nice because now it's an improvement over what we've had before. Because now, if I want to know how many indices I'm going to have at most for a certain length, so let's say I have T postings in total and the standard size is N, so I'm going to have now log of T over N indices. I used to have T over N indices of size N, but now that I have these powers of 2, it's only the log. Why the log? It's exactly the same log that you take when you want to write a number in base 2. If you want to know how many bits you know to write number n, that's the log of n in base 2. You agree with that, right? The log gives you the number of digits in the base that you want. So this is why we have log of T over n. That's the number of indices that I have, which is the number of bits in base 2 of T over n. Okay. So that's great because then that means that when I construct, that gives me a complexity of T log T over n. That's acceptable, right? It's not quadratic anymore. So we have had an improvement, which is the whole point of these LSM tree structures. And the query time is the log of T over n. Why? Because we need to every time look at all of the indices. And since they are log of T over n indices, this is the time it takes to query, right? Okay. So it's a compromise, as you can imagine, between the index construction time and the querying time. That's actually a general wisdom in computer science. If you want to be faster at runtime, then you need to take more time when you prepare the data structures, right? So you cannot you cannot both have the pie and eat it, right? Okay. So surprisingly, and it depends, of course, on the context, but what many search engines actually do is that they just reconstruct the internet periodically, like every 48 hours, they refresh a partition of the internet. So that's actually very, very common as a worldwide search engine to do that. But the other techniques are still very useful, just not at the scale of the internet, right? If you at the scale of a company on your own database and so on, LSM trees are super, super useful. Now, everything I've shown you on how to build larger indices on larger collections, even the whole internet, was with the standard inverted index. But we've seen other kinds of indices, right? We've seen byword indices. We have seen positional indices like this with the positions of the tokens. We have seen permuterms, so many other sorts of indices and modifications. Do you agree that what I've shown you can also be reused for these, right? It's exactly the same idea. This idea of partitioning the collection, processing it partition by partition, and then merging at the end. And it doesn't matter if you do it BSBI or SPIMI locally and sequentially, or if you use MapReduce on a cluster of machines and you process the partitions in parallel, right? So this is exactly the same idea. You just need to adapt the algorithm a little bit. Maybe I should say, because maybe that wasn't clear for MapReduce, somebody asked at the break, what the map function does and what the reduce function does in the map phase and in the reduce phase is entirely customizable. That's up to the user to say that. So when you connect to a cluster of machine of machines and you want to execute a MapReduce job, you say the map function that you want and you say the reduce function that you want. And then the cluster is going to do it, right? And of course, the map function and the reduce function for indexing the web is not going to be the same map function and reduce function as for counting Pokemons. And it's not going to be the same map and reduce functions that you're going to use when you want to multiply matrices, right? So this is entirely customizable. And this is, in fact, the reason why MapReduce is so popular, because it's both very simple and very generic at the same time, right? And it's so simple and generic that MapReduce was at the basis, and it's the fundament of newer technologies that were created. Who knows Apache Spark? Who heard of Spark? Apache Spark? Who never heard of Spark? Some of you, right? But at least there was a few more raised hands than MapReduce, right? So Spark can be seen as a newer generation of MapReduce that both makes it more user-friendly, and it also allows you to orchestrate several rounds of map shuffle reduce. Okay. Very good. Yes, I wanted to say this is basically a transition to what is going to come a little bit later, is that what we have here in our index has sorted, we have sorted documents, right? Sorted by document ID, so this posting list. And this is great for Boolean querying. But that doesn't give us yet the ranking of the web pages, right? So it sounds like we've built a Google, but we haven't built a Google yet. We have built a Google that is able to download the entire web and index the entire web. However, the Google we've built just returns you a set of web pages without any ranking, right? So we are not there yet, right? Google is able to tell you the first 10 pages with some scoring system. And that we don't have yet. We'll have to build that in a couple of weeks, right? So that's what I meant, that we don't have yet any ranking. We just return sets of web pages. And we don't address security at all just yet, right? So you also might need to worry as a company about who has the right to access or see that data. For example, the legal companies that might have some sensitive data. So this is the chapter 4 of the book. Who has read the first 3 chapters of the book? Very good. Who has already read chapter 4? Who will read chapter 4? Very good. Okay, so you should. That's basically what I've explained to you, but with another angle, and then you can take the time to read through the chapter. And of course, you can watch the recording. I know you do it with plus 25% speed or something. So that's the purpose. Do we have any questions on index construction? Questions on Zoom? Any questions? Also not on Zoom? Okay. So let's then move to the next part on index compression. So I'm going to stop the recording here and see you on the other side.